Okay, so we have a circuit contains a capacitor, a resistor, or power supply. If we put it up into the initial position, that eventually will charge up our capacitor. You don't need to know the maths for that section, okay? You just have to know what it gets charged up to. We're interested in the maths once we flick that switch into the lower position. But what we should know is that by the time it's fully charged, the voltage on our capacitor is going to be 5 volts, okay? Only then will we kind of throw the switch. So it asks us a number of things. First thing it asks for is the time constant for the circuit. So time constant is equal to the resistance times the capacitance, which is equal to 1 by 10 to the 3 multiplied by 200 by 10 to the minus 6. Type that into your calculator. And it gives us 0.2 seconds. Okay, so what we're saying is once we discharge that, it will take 0.2 seconds for it to fall to 0.37 roughly of its initial value. That should kind of give you an indication when you're calculating an answer what the answer is going to roughly be. Because if I know it's kind of about 0.4 seconds ish, I know that's going to be 0.3 times 0.3. It's going to be a very small value. Before we can start working out anything, we have to work out what the initial values will be for each of these things. So we know that the initial value, once we start discharging, for the voltage is going to be 5 volts. Okay, there's always a supply voltage if it's fully charged. We can then work out Q naught because Q equals CV. So we're dealing with the start. It's just going to be 200 by 10 to the minus 6 times 5, which is 1 by 10 to the minus 3 coulombs. Now, when we throw it down to the lower position, initially it will have this much push from the capacitor. The resistance here is 1 kilo ohm, so we can do V equals IR. But looking at the initial values, so the initial current is going to be V divided by R, which is 5 divided by 1000, so it's just 5 by 10 to the minus 3 amps. That's about all that's new. Okay, everything else then after that just acts the same way as our radioactive decay that we were looking at before. It's understanding the circuit enough to get both your time constant, so you can put it into the equations, and these 3 initial values that allow you then to access the questions. Question 3 then asks for the current after 1.5 seconds. So we're trying to find I after time of 1.5 seconds. We're going to be using I equals I naught e to the minus t over tau. Put in our values. I equals I naught, 5 by 10 to the minus 3. E to the minus 1.5 divided by our time constant, which is that. Always just be careful when you're typing that into your calculators that you include the minus with the E. Okay, we are expecting this to decrease. And it should give you 2.77 by 10 to the minus 6 amps. Okay, any questions up to there? Last thing, more complicated, is how long will it take for the voltage across the capacitor to fall to 1.5 volts? So we're now looking for the time. When the voltage will be, was it 1.2? Yeah, 1.2 volts. So we're dealing with voltage, so we just use V equals V naught e to the minus t over tau. 1.2, the initial voltage was 5, equals e to the minus t over 0.2. Divide both sides by 5, gives you 0.24, equals e to the minus t over 0.2. Everybody should get up to that step relatively easy. What's our next step then? Take natural logs. Okay, so we take a natural log of this side and a natural log of the other side. Natural log of 0.21 is minus 1.427. We take the indice in front of the log, which will give us minus t over 0.2 equals natural log e. What's the natural log of e? 1, so we can just ignore that. So it gives us that t is equal to 0.2 times 1.427, and it gives us that will be 0.285 as time, so it's in seconds.